double filtration plasma pherises. Both plasma filter and EVA flux are being primed now in different machines with different sets. The person behind the effort we see here, Dr. Girish Kumtekar. The circuit of the patient is now connected. The arterial end goes through the plasma filter. The drain of the plasma filter, as you can see here, is now connected to the EVA flux. This will be now connected to the EVA flux. The venous end from the plasma filter goes back to the patient. This is the venous chamber that we see here. From the EVA flux, the venous end of the EVA flux, the arterial end is connected to the exit side, the drain of the plasma filter. The venous end of the plasma filter is clamped, and the chamber from the venous end is connected back to the venous chamber of the plasma filter to facilitate the passage of a kind of replacement fluid from the EVA flux. Also, independently, replacement fluid in the form of saline, albumin and IVIG is connected back to the patient through a separate venous line, connected at the venous end through a three-way into the palm cath of the patient. So this is the DFPP circuit which is connected here. The arterial line going through the pump to the plasma filter, the venous end of the plasma filter, which is returned through the venous chamber into the patient. The plasma which is filtered by the plasma filter is connected to a arterial end of the circuit of the EVA flux through the pump. The pump speed of the plasma filter is 150 ml per minute, while the pump speed of the plasma EVA flux is kept around 30 ml per minute. This is because the plasma which is filtered from the plasma filter has to pass through this, so the pump speed is kept at 30 to facilitate slower removal of the plasma. The arterial end of the plasma of the EVA flux goes through the EVA flux filter, and the venous end is clamped. The venous end is, as you can see here, this is the venous end of the EVA flux which is clamped. The idea of clamping the EVA flux venous end is to prevent very fast removal of the fluid, and the venous chamber of the return from the EVA flux is connected to the drain bag to prevent a fast removal of the venous end. It is regulated by a dorsiflow flow at a rate of 200 ml per hour. Now the effluent which comes from the EVA flux, which is supposed to contain all the coagulation factors, the one which we are removing is
only albumin and IVIG.
Albumin and immunoglobulins, whereas the coagulation factors which are removed by the EVA flux are sent back into the patient. The return of the EVA flux, that is from the drain side, is connected to the venous chamber of the plasma filter. This return is kept under high pressure by locking the venous line and by regulating the drain line to less than 200 ml per minute, so that this pressures in this line remain high and there is prevention of the reflux from the venous chamber. So this whole system is now delivers back the coagulation factors back into the patient, while only the immunoglobulins are removed. This is the process of double filtration of plasma pheresis. So this is about the removal of plasma in the process. The drip rate of 200 ml per minute. So how much ever is the fluid that is being, the plasma that is being removed in this bag has to be replaced by a separate peripheral line, the drip rate of which should match the fluid that is being removed. The replacement fluid that is being planned in this patient is RL 500 ml, albumin of 100 ml and IVAG of 100 ml. So total 700 ml approximately is the planned removal of plasma and replacement. So RL will be given first, and the last half an hour of the process, it's a total 3-hour process. The last 3 hours, the last half an hour, replacement of albumin and IVIG is being planned so that these are not lost during the process of plasma pheresis. This DFPP is followed by a dialysis so that extra fluid of around 1 liter is removed. So the DFPP on alternate days with dialysis is repeated for a period of 3 to 4 sessions, after which we expect the titers of anti-A to come down, anti-A bar anti-B to come down to 1 in 4, after which the patient will be taken up for transplantation. The last DFPP is also followed by replacement of plasma to prevent a bleeding risk perioperatively. Post-transplant rescue DFPP can be done if titers go beyond 1:32. This is the typical plasma flux that we see here. It's a Fresenius polysulfone membrane. It has a TMP max of around 100 mm of mercury. This is the EvaFlux plasma fractionator, which helps in removal of separation of immunoglobulins and albumin from the coagulation factors predominantly. Can't find the membrane type here.